Listening practice, an expanded, detailed outline for Chapter 1, Introduction to AI and Robotics, including key themes, examples, and thought-provoking questions to frame the narrative. Chapter 1, Introduction to AI and Robotics 1.1 The convergence of AI and robotics, defining the synergy, how AI algorithms, machine learning, neural networks, empower robots to adapt, learn, and make decisions in dynamic environments. Contrast with traditional robotics, pre-programmed automation versus AI-driven autonomy. Key technologies bridging the fields, computer vision, e.g., Tesla's autopilot. Natural language processing, e.g., OpenAI's ChatGPT integrated into robot assistants. Reinforcement learning, e.g., robots mastering complex tasks like folding laundry. Case studies, self-driving cars, Waymo's AI navigating unpredictable traffic. Delivery drones, Ziplin's AI-powered medical supply drones in Rwanda. Societal impact, job markets reshaped by collaborative robots, cobots. The rise of smart homes and cities. 1.2 Historical milestones, from Turing to Boston Dynamics, early foundations, mechanical automata, e.g., 18th century mechanical Turk. Alan Turing's 1950 paper Computing Machinery and Intelligence and the Turing Test, Robotics Breakthroughs, 1961, Unimate, the first industrial robot. 1966, Shaky, the first mobile robot with AI perception. 2000s, Honda's Asimo and the quest for bipedal locomotion. AI's evolution, 1956, Dartmouth Workshop and the birth of AI as a field. 1997, IBM Deep Blue defeats chess champion Garry Kasparov. 2012, AlexNet revolutionizes deep learning and computer vision. Modern icons, Boston Dynamics Spot, 2015, and Atlas, 2016 redefining agility in robotics. OpenAI's DALLE and GPT-4, 2023 generative AI's creative leap. Timeline graphic, visualizing the parallel growth of AI theory and robotic hardware. 1.3 Ethical and economic implications of autonomous systems, ethical dilemmas, bias in AI, how flawed training data perpetuates discrimination, e.g., facial recognition errors. Privacy, surveillance robots in public spaces, e.g., Dubai's police robots. Accountability, who is liable when a surgical robot or self-driving car fails. Economic shifts, job displacement, McKinsey's prediction of 800,000 jobs lost to automation by 2030. New opportunities, emerging roles in AI ethics, robot maintenance, and data science. Global inequality, will AI widen the gap between tech-savvy and developing nations? Policy and governance, EU's AI Act, 2023 risk-based regulation of AI systems. US versus China, competing visions for AI dominance. Provocative debates, should robots have legal personhood? Universal basic income, a solution to AI-driven unemployment. Chapter 1 Discussion Questions 1. Can AI ever truly replicate human intuition, or will robots always lack common sense? 2. How might the convergence of AI and robotics redefine what it means to be employed? 3. Should governments prioritize AI innovation over potential job losses? Key visuals for Chapter 1, Infographic, the feedback loop between AI advancements and robotic capabilities. Timeline, from ancient automata to Neuralink. Concept map, ethical trade-offs in autonomous systems. This chapter sets the stage for deeper dives into specific innovations, like Tesla Optimus or surgical robots, while grounding readers in foundational debates. Let me know if you'd like to refine any section or add case studies. Here's an expanded, engaging outline for Chapter 2, The Evolution of Humanoid Robots, blending technical innovation, societal debates, and real-world applications. Chapter 2, The Evolution of Humanoid Robots 2.1 From Asimo to Optimus Gen 2, a timeline of humanoid design, Early pioneers, 2000, Honda's Asimo debuts, mastering bipedal walking and stair climbing. 2013, DARPA Robotics Challenge sparks advancements in disaster response robots. 2016, Boston Dynamics Atlas performs parkour, redefining agility. Modern era, 2021, Tesla unveils Optimus prototype, Bumblebee, a rudimentary bipedal bot. 2022, Xiaomi's Cyber 1 emphasizes emotional AI and consumer interaction. 2023, Optimus Gen 2 launches with Tesla's biological-inspired design. Key design shifts, from rigid hydraulics to lightweight actuators. AI replacing pre-programmed motions with real-time adaptability. 2.2 Tesla Optimus Gen 2, engineering breakthroughs. 2.2.1 Mobility and tactile sensing, mimicking human movement. Hardware innovations, Tesla designed actuators for fluid, energy-efficient motion. Tactile sensors, fingertip pressure feedback for delicate object manipulation, e.g., holding an egg. Balancing algorithms, neural networks trained on human motion capture data. Case study, Optimus Gen 2 assembling a Tesla vehicle battery versus human workers. 2.2.2 AI-driven task execution, from factories to households, autonomy stack, Tesla's full self-driving, FSD, software adapted for robot navigation. Multimodal learning, combining vision, touch, and voice commands. Applications, industrial, warehouse logistics, hazardous material handling. Domestic, elderly care, cooking, and childcare, controversial. Limitations, handling unstructured environments, e.g., cluttered homes. 2.2.3 Ethical debates, will robots replace human labor? Pro-robot arguments, dangerous/dull tasks delegated to robots, e.g., mining, assembly lines. Upskilling workers to manage AI systems. Counterarguments, McDonald's experiment, robot fry cooks displacing entry-level jobs. Global South exploitation in robot manufacturing supply chains. Middle ground, cobot, collaborative robot, models, humans and robots working side by side. 2.3 Competing humanoids, Xiaomi Cyber 1 vs Agility Robotics, Xiaomi Cyber 1, focus, emotional intelligence and consumer appeal. Features, AI emotion recognition via cameras/microphones. Mi Sense spatial awareness for interactive tasks. Target market, retail, entertainment, and personal companionship. Agility Robotics Digit, focus, logistics and real-world utility. Features, bird-like legs for dynamic stability on uneven terrain. Payload capacity of 40 pounds, ideal for last-mile delivery. Partnerships, Amazon's warehouse pilot program. Head-to-head comparison, metric Optimus Gen 2 Cyber 1 Digit AI capability multitask autonomy emotional interaction task-specific focus mobility human-like dexterity limited to flat surfaces quadruped agility cost $20,000, projected, $100K plus $250K plus primary use case manufacturing/domestic consumer-facing roles industrial logistics Chapter 2. Discussion Questions 1. Should humanoid robots prioritize human-like appearance over functional efficiency? 2. How might emotionally intelligent robots, like Cyber 1, impact mental health and social dynamics? 3. Is a universal humanoid feasible, or will robots remain niche specialists? Key visuals, timeline graphic, major humanoid robots, 2020-30. Diagram, Tesla Optimus Gen 2's sensor and actuator layout. Side-by-side video clips, Optimus vs Digit performing warehouse tasks. This chapter balances technical depth with ethical nuance, encouraging readers to reflect on the trajectory of humanoid robotics. Let me know if you'd like to add more case studies or refine comparisons. Here's a structured and engaging expansion of Chapter 3, AI for Global Challenges, designed to inform and provoke critical thinking while highlighting real-world applications. Chapter 3, AI for Global Challenges 3.1 Climate Science Meets Machine Learning, The Data Revolution, Big Data Integration. AI processes petabytes of climate data from satellites, e.g., NASA's Earth Observing System, ocean buoys, and ice core samples. Key applications: carbon emission tracking. Platforms like Climate Trace use AI to pinpoint global emission sources in real time. Ecosystem modeling, predicting Amazon rainforest degradation using reinforcement learning, e.g., Microsoft's AI for Earth. Case studies: ice melt predictions. DeepMind's AI model forecasting Greenland ice sheet loss with 90% accuracy. Coral reef preservation. AI-driven drones monitoring reef health and identifying bleaching events. Collaborations, partnerships like Google x UNEP to map global air quality and methane leaks. 3.2 Google DeepMind's GraphCast, revolutionizing weather prediction. 3.2.1 How GraphCast outperforms traditional models. Technical innovation, graph neural networks, GNNs analyzes global weather as interconnected nodes. Unlike traditional numerical weather prediction, NWP, grids. Speed, produces 10-day forecasts in under 60 seconds versus hours for NWP. Accuracy, reduces error rates by 20–50% for metrics like hurricane trajectory prediction. Training data, 40 years of historical weather data from the ERA5 dataset. 3.2.2 Case study, predicting extreme weather events. Hurricane Lee, 2023, GraphCast predicted landfall 48 hours earlier than the European Centre for Medium-Range Weather Forecasts, ECMWF. Enabled earlier evacuations in Nova Scotia, potentially saving hundreds of lives. European heatwave, July 2023, forecasted temperature spikes 10 days in advance, aiding energy grid preparedness. 3.2.3 Limitations and the path to global adoption. Challenges, data gaps, sparse historical records in developing nations limit model reliability. Explainability, black box nature raises trust issues among meteorologists. Computational costs, requires cloud infrastructure inaccessible to low-income countries. Solutions, open source initiatives like WeatherBench for collaborative model refinement. Hybrid models combining GraphCast with local NWP systems. 3.3 AI in disaster response, wildfire mapping and flood forecasting, wildfire management, AI tools, NASA's firms, satellite-based fire detection with machine learning to predict spread using wind/topography data. Dryad networks, solar-powered sensors detecting forest fires within 60 minutes. Case study, 2023 Canadian wildfires. AI-guided drones prioritized firefighting in Alberta's Jasper National Park. Flood forecasting, Google's Flood Hub, covers 80 countries, using AI to predict floods 7 days in advance, e.g., 2023 Kerala floods. Integration with IoT, river sensors in Bangladesh send data to AI models via low-bandwidth SMS. Ethical considerations, data privacy, balancing crisis mapping with citizen surveillance concerns. Equity, ensuring AI tools reach vulnerable communities without digital infrastructure. Chapter 3 Discussion Questions 1. Should AI climate models prioritize accuracy over interpretability to meet urgent environmental deadlines? 2. How can global tech firms ensure equitable access to AI disaster tools in the global south? 3. Could over-reliance on AI predictions reduce human preparedness for unforeseen crises? Key visuals, infographic, how GraphCast's node-based system outperforms grid models. Map overlay, AI predicted versus actual Hurricane Lee path, 2023. Photo essay, AI drones in action during Canadian wildfires. This chapter underscores AI's transformative potential in tackling existential threats while urging caution against technological overreach. Let me know if you'd like to explore specific tools or regional case studies in greater depth. Here's a comprehensive, thought-provoking expansion of Chapter 4, AI-powered surgical robotics, blending technical innovation, real-world applications, and ethical discourse. Chapter 4, AI-powered surgical robotics 4.1 The rise of minimally invasive surgery, MIS, paradigm shift, transition from open surgery to laparoscopic and robotic techniques, reducing patient trauma and recovery time. Role of AI, enhancing precision in suturing, tissue differentiation, and complication prediction. Key drivers, patient demand, 70% shorter hospital stays for robotic prostatectomies versus traditional methods. Surgeon ergonomics, reduced physical strain with robotic arms, e.g., tremor filtering. Pioneers, 1985, first robotic surgery, Puma 560 for neurosurgery. 2000, Da Vinci surgical system gains FDA approval, dominating the field for 2 decades. 4.2 Johnson & Johnson's Ottava, precision in the operating room 4.2.1 machine vision and real-time decision-making, tech stack, 8K 3D imaging, high-resolution cameras with AI-powered tissue recognition, e.g., distinguishing tumors from healthy tissue. Force feedback sensors, adjusts pressure in real time to prevent vascular damage. Neural networks, trained on 100,000 plus surgical videos to predict complications, e.g., bleeding risks. Example, Ottava's AI flagged a hidden artery during a colorectal surgery at Mayo Clinic, 2023, preventing a hemorrhage. 4.2.2 Case study, robotic-assisted heart surgery, patient profile, 58-year-old with atrial fibrillation and mitral valve regurgitation. Ottava's role, AI mapped cardiac electrical pathways to guide ablation. Robotic arms performed microsutures with 0.1 mm precision. Outcome, surgery time reduced by 25%, patient discharged in 3 days, versus 7-day average. 4.2.3 Training surgeons in the age of AI, simulation platforms, J&J's Touch Surgery, AR app using AI to simulate complex procedures. Adaptive learning, AI tailors training modules based on surgeon skill gaps. Controversy, over-reliance on AI may erode manual surgical expertise. Pro-argument, AI democratizes access to elite techniques for rural hospitals. 4.3 Competing systems, Da Vinci Xi versus Medtronic Hugo, Intuitive Surgical's Da Vinci Xi, strengths, proven track record, 1.2 m and procedures annually. AI integration, instrument tracking with predictive analytics, e.g., suture fatigue alerts. Limitations, high cost, $2M/system, $2K/disposable tools. Closed ecosystem restricts third-party tool integration. Medtronic Hugo, innovations, modular, portable design or flexibility. Touch Surgery Live, AI overlays real-time guidance via headset. Case study, Hugo reduced hysterectomy costs by 30% in Brazilian hospitals, 2023. Head-to-head, metric Da Vinci Xi Ottava Hugo AI capabilities predictive maintenance real-time tissue analytics AR guided navigation cost $2M plus $1.5 million, estimated, $1 million specialization urology, gynecology cardiac, general surgery gynecology, orthopedics Chapter 4 Discussion Questions 1. Should AI surgical systems require human override capabilities, even if they outperform surgeons? 2. How can hospitals in low-income countries avoid becoming testing grounds for unproven robotic systems? 3. Will AI erode the surgeon-patient relationship, or enhance trust through precision? Key visuals, infographic, AI's role in the surgical workflow from pre-OP planning to recovery. Timeline, Evolution of Surgical Robotics, 1985-2025. Side-by-side video, Da Vinci vs. Ottava performing suturing tasks. Ethical considerations, bias in training data, underrepresentation of diverse patient demographics in AI models. Liability, legal frameworks for AI errors, e.g., Germany's robot judge precedents. Transparency, should patients know if an AI system assisted their surgery? This chapter balances groundbreaking advancements with critical ethical reflection, urging readers to envision a future where AI and human skill coexist in medicine. Let me know if you'd like to add more case studies or technical deep dives. Here's a detailed and engaging expansion of Chapter 5, Beyond Humanoids AI in Everyday Robotics, structured to highlight transformative applications, ethical considerations, and real-world impact. Chapter 5, Beyond Humanoids AI in Everyday Robotics 5.1 Agricultural Robots, AI for Sustainable Farming, Technological Innovations, Autonomous Tractors. John Deere See and Spray uses computer vision to target weeds, reducing herbicide use by 90%. AI drones. Startups like FarmWise deploy drones with multispectral imaging to monitor crop health and optimize irrigation. Robotic harvesters. Agrobot's SW6010 picks strawberries with AI-guided arms, minimizing bruising and waste. Case studies. Vineyard Precision. California's Went Vineyards uses NIO Technologies robots for autonomous weeding and soil analysis. Vertical farming. Iron Ox integrates AI with hydroponic robots to grow leafy greens with 95% less water. Sustainability impact. AI reduces chemical runoff and soil degradation while boosting yields by 20–30% in pilot projects. Challenges. High upfront costs for small-scale farmers. Data privacy concerns over farm-specific AI models. 5.2 Warehouse automation. Amazon's Proteus and Symbotic. Amazon Proteus, AI navigation, uses reinforcement learning to safely navigate around human workers, lifting and moving carts up to 800 pounds. Collaborative workflow, integrates with Robin and Cardinal robotic arms to sort and pack 1,000 items/hour. Symbotic's AI systems, 3D scanning and sorting. AI algorithms categorize items by size, weight, and fragility in Walmart's distribution centers. Efficiency gains, reduced Walmart's restocking time by 40% in 2023 pilot programs. Labor dynamics, job shifts. While repetitive roles decline, demand rises for robot maintenance technicians and AI supervisors. Controversy. Union pushback against Amazon's lights-out warehouses with minimal human oversight. Future trends. Swarm robotics, coordinated fleets of micro-robots for rapid inventory management. Predictive restocking, AI forecasting consumer trends to auto-replenish stock. 5.3 Consumer robotics, companion bots and AI pets. Emotional AI companions. Sony Abo, uses deep learning to recognize faces, respond to 100+ voice commands, and learn household routines. GrooveX's Love It, cuddle-driven robots with thermal sensors to seek human warmth, reducing loneliness in elderly users. AI Pets. Miroi, biomimetic robot dog with AI mimicking animal behavior, used in dementia therapy. Zoomer's AI Pals, interactive toys that evolve personalities via natural language processing. Ethical considerations, privacy risks, always-on microphones/cameras in homes, e.g., Samsung's Bot Handy. Emotional dependency, studies show 30% of elderly users develop attachment to companion bots, raising ethical concerns about human replacement. Market growth, projected $15 billion industry by 2030, driven by aging populations and smart home adoption. Chapter 5 Discussion Questions 1. Should governments subsidize AI agricultural tools for small farms to ensure equitable access? 2. Do companion robots risk deepening social isolation, or are they a necessary solution for caregiver shortages? 3. How can warehouse automation balance efficiency with humane labor practices? Key visuals, infographic, AI's role in the farm-to-table supply chain. Photo essay, A Day in Amazon's Proteus-powered warehouse. Comparison chart, popular companion bots, Abo vs Loveit vs Miroi. Ethical and future outlook, bias in agri-AI, training data often skews toward Western crops, neglecting tropical farming needs. Regulation, EU's proposed AI liability directive to hold firms accountable for robotic errors. Next-gen trends, footprint robots, AI calculating carbon footprints of meals in real time. Morphing robots, MIT's shapeshifters adapting from delivery drones to shelf stockers. This chapter illustrates how AI-driven robotics is reshaping industries and daily life, urging readers to weigh technological promise against societal responsibility. Let me know if you'd like to explore specific robots or regional impacts further. Chapter 6, Ethical Frontiers 6.1 Bias in AI Decision-Making, Who's Accountable? Defining AI bias, systemic errors in AI outputs due to skewed training data, flawed algorithms, or lack of diversity in development teams. Example, facial recognition systems misidentifying people of color, e.g., 2018 MIT study showing 34% error rate for darker-skinned women versus 0.8% for lighter-skinned men. Case studies, Amazon's hiring algorithm, 2018 discriminated against female candidates by downgrading resumes with words like Women's Chess Club. Compass recidivism tool, 2016 predicted black defendants as higher risk at twice the rate of white defendants. Accountability frameworks, legal liability, should developers, companies, or end users bear responsibility? Algorithmic audits, tools like IBM's AI Fairness 360 or Google's What If tool to detect bias. Diverse teams, inclusive development practices to mitigate blind spots. Solutions, transparency, mandating right to explanation for AI decisions, e.g., EU GDPR. Bias bounties, crowdsourced testing for vulnerabilities, as pioneered by OpenAI. Ethical considerations, can fair AI exist in inherently biased societies? Should AI systems be allowed in high-stakes domains, e.g., policing, without bias mitigation? 6.2 Privacy concerns, robots in public and private spaces, data risks, surveillance robots, security bots like Nightscope mapping public spaces, raising fears of mass data collection. Consumer devices, iRobot's Roomba sharing floor plans with Amazon, 2022 controversy. Case studies, Boston Dynamics Spot, used in Singapore parks during COVID-19 to enforce distancing, sparking privacy debates. Elderly care bots, companion robots recording sensitive health data vulnerable to breaches. Regulatory responses, GDPR compliance, requiring explicit consent for data collection by robots in the EU. CCPA in California, granting users rights to delete data from home robots. Technological safeguards, edge computing, processing data locally on robots to reduce cloud vulnerabilities. Anonymization, stripping identifiable info from datasets used for AI training. Ethical debates, balancing public safety, e.g., disaster response drones, versus individual privacy. Should robots in homes have off switches for data collection? 6.3 Global regulations, EU AI Act and beyond, EU AI Act, 2023, risk-based framework, prohibited AI, social scoring, real-time biometric surveillance in public spaces. High-risk AI, hiring, healthcare, and law enforcement systems requiring strict audits. Transparency rules, chatbots must disclose non-human identity. Global responses, U.S. sectoral laws, Algorithmic Accountability Act, 2023, targeting hiring and housing. China's AI ethics guidelines, state-controlled AI development with emphasis on core socialist values. OECD principles, voluntary frameworks for transparency and accountability. Challenges, extraterritorial impact, EU rules affecting global tech firms, e.g., fines up to 6% of revenue. Enforcement gaps, developing nations lacking resources to monitor compliance. Future trends, harmonization efforts, unled initiatives for global AI standards. Certification systems, ISO standards for ethical AI akin to organic food labels. Chapter 6 Discussion Questions 1. Should AI developers face criminal penalties for biased systems causing harm? 2. How can societies balance the benefits of public safety robots with the right to anonymity? 3. Is the EU's strict regulatory approach a model for the world, or a barrier to innovation? Key visuals, infographic, how bias infiltrates the AI life cycle from data to deployment. World map, comparing AI regulations in the EU, US, China, and Brazil. Flowchart, data pathways in home robots where your privacy could leak. Ethical outlook, AI for good versus AI for control, tension between humanitarian applications, e.g., disaster relief, and authoritarian misuse, e.g., surveillance states. Grassroots movements, campaigns like Stop Killer Robots advocating for bans on autonomous weapons. This chapter challenges readers to confront the moral complexities of AI and robotics, emphasizing the need for proactive governance and inclusive innovation. Let me know if you'd like to explore specific regulations or case studies further. Chapter 7, The Future of AI and Robotics 7.1 Quantum AI, Next-Gen Computing for Robotics, Quantum Computing Primer, qubits and superposition. Unlike classical bits, qubits exist in multiple states simultaneously, enabling exponential computational power. Entanglement, linked qubits allow instantaneous correlation, revolutionizing data processing. Quantum AI applications, optimization, solving complex logistics, e.g., robot pathfinding in dynamic environments, via quantum annealing, D-wave systems. Machine learning acceleration, Google's TensorFlow Quantum trains AI models 100x faster for real-time robotic decision-making. Case studies, NASA's Quantum AI Lab, simulating Mars rover navigation scenarios with hybrid quantum classical algorithms. Volkswagen traffic optimization, quantum AI reduced traffic congestion by 20% in Lisbon using real-time data from autonomous vehicles. Challenges, error rates, qubit decoherence limits practical scalability. Hardware constraints, cryogenic cooling requirements hinder integration into mobile robots. Future outlook, quantum cloud robotics, AWS Braket and IBM Quantum enabling remote quantum processing for swarm coordination. 7.2 Swarm intelligence, coordinated drone networks, principles of swarm robotics, decentralized control, inspired by ant colonies and bird flocks, using local interactions, stigmergy, for global coherence. AI algorithms, genetic algorithms and reinforcement learning for adaptive behavior. Applications, disaster response, drones mapping earthquake zones, e.g., Zipline delivering medical supplies in Rwanda. Agriculture, swarm farm robotics deploying 100+ drones for precision pesticide application. Military and ethical concerns, DARPA's Offset program, autonomous drone swarms for urban warfare, raising debates on AI-driven warfare ethics. Innovations, Harvard's RoboBees, solar-powered micro-drones for pollination. Exxon Technologies, autonomous drone swarms mapping mines without GPS. Challenges, scalability, ensuring coordination in swarms of 1,000+ units. Security, vulnerability to cyber attacks disrupting swarm behavior. 7.3 Brain-computer interfaces, merging humans and machines, BCI technologies, invasive versus non-invasive, Neuralink's chip implants versus OpenAI's EEG headsets. Signal types, electrocorticography, ECOG, for high-resolution neural data. Robotics integration, prosthetics, Johns Hopkins Luke arm controlled via implanted electrodes, restoring tactile feedback. Exoskeletons, suits as Phoenix aiding paraplegics to walk using neural signals. Medical breakthroughs, Neuralink trials, 2023 first human subject controlling a computer cursor via thought. BrainGate, ALS patients typing 90 characters/minute with mind-controlled interfaces. Ethical frontiers, privacy, risk of neural data hacking. Human enhancement, debates on cognitive inequality from keys. Future trends, brain-to-brain communication, University of Washington's experiments transmitting thoughts between humans. AI augmented cognition, DARPA's next-gen non-surgical neurotech enhancing memory and learning. Chapter 7 Discussion Questions 1. Could quantum AI render classical robotics obsolete, or will hybrid systems dominate? 2. Should autonomous drone swarms be banned in warfare under international law? 3. How can society prevent keys from widening the gap between enhanced and unenhanced humans? Key visuals, quantum circuit diagram, illustrating qubit entanglement in robot decision-making. Swarm coordination map, drone paths during a disaster response simulation. Neural interface timeline, from early EEG to Neuralink's 2023 breakthroughs. Societal impact and challenges, job market shifts, quantum AI disrupting roles in logistics and cybersecurity. Regulatory gaps, lack of global standards for BCI data ownership. Existential risks, Elon Musk's warning of AI surpassing human intelligence by 2025. This chapter envisions a future where quantum leaps in computing, bio-inspired swarms, and neural interfaces redefine humanity's relationship with technology. It challenges readers to weigh innovation against ethics in an increasingly interconnected world. Here's a structured and comprehensive draft for the appendices and bibliography, designed to complement the book's content while providing readers with quick reference tools and avenues for deeper exploration. Appendices: a glossary of AI and robotics terms, actuator, a motor or mechanism that enables robotic movement. Algorithm, a step-by-step procedure for solving problems or performing tasks. Autonomous systems, machines capable of operating without human intervention, e.g., self-driving cars. Bias, AI systematic errors in AI outputs due to flawed data or design. Computer vision, AI's ability to interpret visual data, e.g., facial recognition. CRISPR, gene editing tool often paired with AI for precision medicine. Edge computing, data processing done locally on devices, reducing cloud reliance. Generative AI, models like GPT-4 that create text, images, or code. Neural network, AI architecture inspired by the human brain. Qubit, basic unit of quantum information, versus classical bit. Swarm robotics, coordination of decentralized robots, e.g., drone fleets. Tactile sensing, robots' ability to feel via pressure or temperature sensors. B key innovators and companies to watch: Tesla, humanoid robots, Optimus, and autonomous vehicles. Google DeepMind, AI for weather prediction, GraphCast, protein folding, AlphaFold. Boston Dynamics, agile robots, Spot, Atlas. Neuralink, Elon Musk brain-computer interfaces. Intuitive Surgical, Da Vinci robotic surgery systems. OpenAI, GPT-4, DALLE, and AI ethics research. Agility Robotics, humanoid robot digit for logistics. IBM Quantum, quantum computing advancements. Climeworks, direct air capture, DAC, for carbon removal. Sila Nanotechnologies, next-gen battery materials. Emerging startups, Bright Machines, AI-driven manufacturing. Neurala, AI for edge devices. Epicor Biosystems, wearable health sensors. C timeline of major breakthroughs, 2020-30, 2000, Honda's Asimo debuts as first advanced humanoid. 2004, DARPA Grand Challenge sparks autonomous vehicle research. 2012, AlexNet revolutionizes deep learning. 2015, Boston Dynamics Atlas performs parkour. 2016, AlphaGo defeats world champion Lee Sedol. 2020, GPT-3 released, showcasing generative AI's potential. 2022, Tesla unveils Optimus prototype. 2023, Neuralink begins human trials. Google's GraphCast transforms weather forecasting. EU AI Act enacted. 2025, projected quantum AI achieves commercial scalability. 2030, projected brain-computer interfaces mainstream in healthcare. Bibliography and further reading. Books 1. Bostrom, Nick. Superintelligence, Paths, Dangers, Strategies, 2014. 2 Tegmark, Max Life 3.0, Being Human in the Age of Artificial Intelligence, 2017. 3 Russell, Stewart. Human Compatible, AI and the Problem of Control, 2019. 4 Lee, Kai-Fu. AI 2041, 10 Visions for Our Future, 2021. Academic Articles and Reports, The Ethics of Artificial Intelligence, Florida et al., Nature, 2021. Global AI Governance, A Blueprint for the Future, Brookings Institution, 2023. The Future of Robotics in Surgery, Lancet, 2022. Quantum Machine Learning, A Review, Biamonte et al., Nature, 2023. Industry Reports, McKinsey & Company. The State of AI in 2023. World Economic Forum. AI for Climate Action, 2023. WHO. Ethical Guidelines for AI in Healthcare, 2022. Websites and platforms, arcs4.org, preprints on AI, robotics, and quantum computing. IEEE Spectrum, latest trends in robotics and AI ethics. MIT Technology Review, in-depth analyses of emerging tech. Features for enhanced usability, hyperlinks, digital edition direct links to cited papers, company websites, and demo videos. QR codes, scan to access supplemental videos, e.g., Optimus Gen 2 in action. Interactive timeline, ebook clickable milestones with expanded descriptions. Let me know if you'd like to refine entries or add niche resources.